again. Thank you. Thank you. Thank you very much. Welcome again to some of you who've been here this morning, and to those who've just arrived, welcome. I'm Lawrence Krauss, Director of the Origins Initiative here, and while I know a number of you were here, I think some of you have just come for the afternoon, so I'll spend a few moments talking about what's been happening here. The Origins Initiative is designed to ask some of the deepest questions that people have ever asked. In fact, in the morning we heard about how people started to ask questions. And when they first started to come up with symbolic language, they probably asked, why am I here and where did I come from? And those are the kind of questions the Origins Initiative is dealing with. And we've had 70 of the world's greatest scientists here over the weekend debating and discussing some of those questions. But this is truly the capstone event. It's bringing together, and I truly believe, the largest accumulation of scientific public intellectuals that have ever been in one place at one time. And we are particularly honored to have them here. And it's been an exciting morning. And also, as I said this morning, I'm particularly proud to be here for so many reasons. But one of the reasons is that we have a 3,000-seat auditorium that's essentially sold out for 12 hours of science. And I think that says something about the people of Phoenix. So I want to applaud all of you. So thank you. It's my great pleasure now to introduce, to welcome you on behalf of Arizona State University, Betty Capaldi, who's the provost of the university. And in case you don't understand what a provost is, in my case, it's very simple. She's my boss's boss's boss. So, okay.
Thank you. Welcome to this absolutely fantastic symposium. It's been a terrific few days of science, and now we're to the public portion. I think this type of event shows why it's so wonderful that ASU is here in Phoenix. I think you know some people have some difficulty understanding the value of a research university. Of course, we educate the students, which is part of this event. They did an event at high school this week, and our students can see this, and we're also being broadcast on the World Wide Web. But bringing the most cutting-edge minds on the most important ideas of the day to Phoenix, and to have a public event so that you can learn about these issues and be up to date, because you influence policy, you influence decisions, and we really appreciate that you all came here for this event. This afternoon is going to be very exciting. We have first some discussions by Richard Dawkins, and then Craig Ventnor and Lawrence Krauss. Lawrence, who you just saw, is the creator of this entire event and has done just a fantastic job. And then Ira Flato will moderate a panel with 6 Nobel laureates. So I know you will enjoy it and be very well informed. Thank you very much for coming. Lawrence is coming back now.
Thank you. Thanks, Betty. Thank you very much. Thank you. Thank you. Well, as I indicated, before the break, we had a dialogue, and we're going to have one after the break, so it's not all lectures. And I'm very pleased to introduce first my colleague and friend, Paul Davies, who is a very distinguished physicist in his own right, and also popularizer of science as well, and is probably well known to people here and everywhere. And I owe him a special debt of gratitude because, in fact, about a year and a half ago, he invited me to come here to give a lecture, and that led to my moving here. And his presence here, in fact, was a huge factor in attracting me. So I'm very happy to introduce Paul Davies.
Well, ladies and gentlemen, good afternoon, and welcome to the second major session of this spectacular series of presentations. And it's my honor and pleasure to welcome back to the Gamage Auditorium Professor Richard Dawkins. Richard was here last year. Some of you may have attended his presentation when he spoke as the 2008 Beyond Annual Lecturer on the theme of his latest book, The God Delusion. So Richard recently retired, would you believe, although he tells me that doesn't mean very much, as the first Charles Simonyi Professor of the Public Understanding of Science at Oxford University, where he's also a Fellow of New College. I think Richard is arguably the foremost science communicator in Britain and possibly the world. His best-selling books are bought in their millions, and you'll know the titles like The Selfish Gene and The Blind Watchmaker. They've influenced a huge number of people. His twin scientific and literary accomplishments are recognized by the fact that he's both a Fellow of the Royal Society and a Fellow of the Royal Society of Literature. His eagerly awaited next book, The Greatest Show on Earth, The Evidence for Evolution, will be published later this year, and I do hope he can make a return visit as part of the launch of that book. I should also mention that he, a few years ago, set up the Richard Dawkins Foundation for Reason and Science. The way this is going to work, Richard doesn't have a prepared presentation. Instead, we're going to adopt the format that Lawrence and Brian Greene did before lunch, that we're going to have a conversation. I think and expect and hope it'll be a somewhat one-sided conversation. My job is just going to be to lead the discussion. So without further ado, could I ask everyone here to welcome Professor Richard Dawkins. Well, Richard, again, welcome back, and it's always a pleasure to talk to you. And this is, of course, an Origins Symposium, and I guess the particular Origins theme that is uppermost in our minds this year is the origin of species, because Darwin's famous book was published 150 years ago. I think most people must know that, and indeed Arizona State University has a year-long Darwin Fest to celebrate that. You are the master expositor, and I know that you can do the job. Can you give us a sort of one-minute summary of the core theme that, that Darwin brought? What is the essence of his theory of evolution, in case people don't know?
Well, let me play for time by beginning by apologizing for my attire. I don't get a chance to wear my Hawaiian shirt in Oxford, and so... Right, one minute on Darwin's theory of evolution. It's why we all exist, it's why we are the way we are, where we means all animals, plants, bacteria, fungi, etc. It is descent with modification was Darwin's phrase, starting with something very simple, the origin of life, and gradually branching, diverging, becoming more and more complex as the generations go by. So it's change over generations, with branching of generations, branching of pedigrees. The driving force behind it, which is the key point that Darwin added to the theory, he wasn't the first to think of it, the key point is natural selection, which is the non-random survival of randomly varying coded information, where the information is instructions for building bodies, and the bodies carry the coded information, and therefore the information which is best at surviving does survive, and the way in which it achieves that success is by being good at building bodies. That's a modern way of putting it. That wouldn't have been Darwin's way of putting it.
Right, which brings me to the next question, that it wasn't just a done deal, was it? That, oh, there we are, all explained, move on to something else. That this is a theory that's still being elaborated and explored. So if Darwin were to come back today, what could we tell him about how his theory is shaped up and the work that's been done since?
The main thing we could tell him would be about genetics. Darwin, if you ask what was the one thing that Darwin got wrong, it was genetics. He was a child of his time, and so he had the genetics of his time. The modern genetics that we now have became modern in two different steps. The first was Mendel, who was actually a contemporary of Darwin, and it's very sad that Darwin never knew about Mendel's work. It was rediscovered many years later in 1900. That was the first step, and that made genetics, you could call it digital. I mean by that a gene is either present in you or it isn't present. In Darwin's time, people thought that genetic information blended. It was like mixing paternal substance and maternal substance to make a blend which was the child. If it had been like that, then natural selection couldn't have worked. And Darwin knew that. It was pointed out in his time. The solution to the riddle is that heredity is not blending. It's all or none. You either have a gene or you don't. The genes that are in you are discrete particles which you got, each one of them you got either from your father or your mother, and so on back through the generations. So it's particulate digital inheritance. That's the first thing we'd tell Darwin if he came back today. The second thing I think we'd tell him would be that in 1953, the molecular genetics revolution was ushered in, and from that point on we knew that genes are digital even within their very substance. A gene is like a length of computer tape. It really is exactly like a length of computer tape, except that instead of being binary, it's quaternary. That's a stunning result for evolution as well as for everything else. What it means is that every living creature has within every one of its cells a walking archive, a complete archive of digital information about its ancestry, in a sense, it's a coded account, I think you could almost say, of the environments in which the animals or plants' ancestors have lived. Now, that means that we can actually work out the family tree, something that Darwin could only have dreamed of. You can actually, for sure, given a bit more time, a bit more money, a bit more time to look at the detailed genomes of every creature, you could work out exactly who is the closest cousin of whom, the precise family tree, at least as far back as bacteria. After that it starts getting complicated because they start sharing genes I should say before that, they start sharing genes in a rather promiscuous fashion.
It's interesting that you say the one thing Darwin got wrong. Now, was he just lucky, or was he really, really perceptive and clever? Because just about everything that he wrote about, humans coming out of Africa, sexual selection as well as natural selection, the various examples he gave, seemed to be spot on.
Yeah, you can be lucky once or even twice, but Darwin got it right too many times. He wasn't lucky. He was absolutely brilliant.
What was the source of that? Do you think, did he have the right education?
Well,
he didn't really, did he?
The odd thing is, I mean, he was very unmathematical, which is an odd thing. I mean, you'd expect, wouldn't you, that somebody mathematical would have been, would have got it. He was a naturalist. He travelled as a young man. He was immensely observant. He was hugely thoughtful. He really, really burrowed down to get to the bottom of a problem and to really understand it clearly and explain it to other people clearly. He was a deep, deep thinker.
Do you think all that time on the Beagle was good? You know, he had plenty of time to sit and think.
Yes.
Most of us don't have that luxury.
That's true, and that luxury persisted throughout his life because he came of a wealthy family, so he never had to earn his living, and he was therefore free to retire to the country and just think and correspond with people all over the world. He had a huge correspondence with naturalists all over the world. So he never had to go into London and earn his daily crust. He just sat at home and thought and wrote and did some experiments. And on the Beagle too, he had time to think. He didn't actually get the idea of natural selection on the Beagle. That came afterwards.
So one of the things that I struggle to get across to non-scientists is that science isn't just a body of wisdom that's handed down, you know, from teacher to student. It's an ongoing process. There's a huge number of things we don't understand, and at any given time, we scientists are learning just as much as we're teaching. So if a young person was going to go into biological sciences today, what are the hot topics? What are the areas that come out of evolutionary theory that are being investigated? Where might the progress lie in the next 10 years?
Well, I suppose a major piece of progress would be the first starting point before evolution got going in the first place.
We'll come on to that in a moment.
The origin of life would be one very important question, completely unknown at present. Another one, I think, would be what I said earlier about finding out exactly the tree of life, using molecular techniques to compare letter by letter these long tapes to see exactly who's the most closely related to who else. There's a huge amount of work going on that at the moment, using the information technology is what it amounts to. It's the digital information technology of the genes to work out the exact tree of life and lots of other things
So
as well.
you couldn't get away with being non-mathematical now?
I doubt it. I mean, maybe a bit. I think it's often been said as a kind of aphorism that if Darwin were alive today, he certainly would never get a grant to do. He never completed his degree at university.
Did it? Oh no, I realise that. That's right. Yes. Now, about 25 years ago, I was asked to take part in a conference in London called "The Value of Useless Research," and a colleague of mine said I was eminently qualified to talk at this. But also present was Martin Rees, now president of the Royal Society, and I remember a remark that he made, which was that in connection with the theory of evolution, that few would deny its greatness, and yet it had no practical applications. Now that's no longer true, is it?
No.
And by practical applications, I mean, is somebody making any money out of applying Darwinian principles?
Well, I suppose you could say that much of agriculture is applying Darwinian principles and has been for thousands of years. Medicine is becoming, or should be becoming, and is increasingly becoming Darwinian. The fact of antibiotic resistance, the evolution of antibiotic resistance among bacteria, is a totally Darwinian principle. I was very irritated to go into my doctor's waiting room a few months ago and saw a pamphlet which was to encourage people to carry on with their course of antibiotics until the end. And it said, because bacteria are clever. What a missed opportunity to educate people in natural selection. I mean, if I were a patient who read bacteria, I said, of course bacteria aren't clever. That's ridiculous. I'm going to ignore the advice. But if you use it as an opportunity to explain natural selection, it's hugely important. If doctors had thought in Darwinian terms when antibiotics were first invented, they would have guessed that you had to be extremely careful about the evolution of antibiotic resistance.
Then there are these genetic algorithms that people use to design things in engineering, which are really, in effect, based on Darwinian principles.
Yes, there's a whole industry of using Darwinian principles to design power stations, to design diesel engines, to design all sorts of things. What you do is you mutate the instructions for making your power station or your diesel engine nozzle or whatever it is, and then select the ones which are most effective in doing the job that they are. And many genetic algorithms actually invoke sex as well. So you have separate genomes, and then you cross them over in just the same way as chromosomes cross over, and then select the most efficient progeny. And it's been shown again and again that genetic evolutionary Darwinian algorithms for discovering the best way to design something actually get better results. Very interestingly, separate starting points converge on the same result as well.
To a physicist like me, looking at life, it really does look like magic matter. It just is so stupendous, so complex, so clever. All these stupid atoms that just blunder around in a gas like the air molecules in this room are conspiring together to make all these wonderful things happen. But the complexity is daunting. And one of the things that seems to distinguish physics from biology is that physicists like deep, simple, universal underlying mathematical principles, as the sort that Lawrence and Brian Greene were talking about, that apply to everything. Now, obviously, Darwinian evolution is a principle. It's a sort of organizational principle. But will there ever be a time when biologists could write down laws of behavior, laws of motion, if you like, by analogy with the laws of physics? Or are they so completely different that biology simply doesn't lend itself ever to that type of treatment?
I think you put your finger on a very interesting difference. At one level, I suppose natural selection is a fundamental universal which produces something like similar results in all creatures, but the details are always different, and biology is so immensely rich in detail that every species gets its living in a different way. I mean, a huge variety of different ways in which species get their living. And yet there's still, excuse me, there's still the one principle underlying it all, which is that whatever it is they do, whether they fly or swim or grow in the ground and photosynthesize or act as parasites in guts, whatever it is, they are all doing the one same thing, which is maximizing the survival of the DNA that built them in the first place. It's just that there's a huge variety of different ways of doing that maximization, and the details of how they do it are what biologists actually spend most of their time doing.
And at the level of individual organisms, we're never going to have the equation of the cell like we've got the equation of the solar system.
I can't imagine that it would ever come down to that, no.
You touched on already the question that interests me most of all, which is the origin of life. Now, it's curious that Darwin himself refused to be drawn on the question of life's origin. He once quipped that one might as well speculate about the origin of matter. Of course, almost by definition, Darwinian evolution works only when you've got something like a living system for it to work on. But the simplest living thing that we now know, if we take a simple bacterium, even one as simple as what Craig Venter is trying to create in the lab, the minimal cell, is still incredibly complicated. And so it raises this whole question about where did the first one come from? Of course, we may never know, but do you have a favorite theory, a favorite idea?
Let me go back a bit and say what the favorite theory would have to do. Once natural selection gets going, then in a sense it's all plain sailing after that. We know how that works. We know that once natural selection gets going, you can derive all living creatures, however complicated, and there seems to be no limit to the complexity that can arise. But it's got to get going in the first place. And the key first step that you've got to have in order for natural selection to get going is some form of heredity. There has to be something corresponding to DNA, information which gets passed from generation to generation with a very high degree of accuracy. DNA does exactly that, but DNA is much too complicated to be the original self-replicating entity that started it off. I don't know whether you agree with that, but I think it's clear that there had to have been some precursor. DNA must have been put together originally by something like Darwinian natural selection, but it couldn't have been the basis for that original natural selection because obviously it had to have been already there. So what we're looking for is a much simpler system of heredity which was simple enough to arise spontaneously from the ordinary laws of chemistry acting in whatever the conditions were in the early Earth. And this has been called, or there has been called, the catch-22 of the origin of life, that DNA is complicated enough to as it were, broker its own propagation, but it's too complicated to have started the process off. And yet if you think of a simpler system, it's unlikely to have been sufficiently high fidelity to have been the medium of natural selection. Somehow we've got to think of a way around that catch-22.
Do you think, at the very least, it's something that was quite likely or highly unlikely? Have you got an inkling? I know this is an unanswered question.
Yes.
But after a lifetime of pondering these things, would you expect that if we could go back to the prebiotic phase on Earth, 3.5, 4 billion years ago, whatever it was, and let it happen again, that life would pop up?
I think it's a profoundly interesting question. It's a tantalizing question. It amounts to the same question as, do we think there's life on other worlds?
Right.
Because if life arose on Earth as a supremely improbable event, then we could say maybe it only arose here. Maybe it arose nowhere else in the universe. If, on the other hand, you go back in your time machine to the primeval soup and say, how likely was it that life would originate? If it was likely, then it presumably must have happened on other planets as well, and so the universe should be teeming with life. I you asked me what my intuitive feeling is. I'm not sure that I should venture an intuition. I'm very interested in both possibilities. If we are literally unique, if this is the only planet in the universe that has life, then it seems to me that it has at least one very interesting consequence, which is that the origin of life must have been so improbable that any attempt to work out how it happened using chemical intuition or chemical experiment or modeling is doomed to failure. We are completely and utterly wasting our time trying to work out how life originated if it's so improbable that it only arose once in the universe. That's not my intuition. I don't believe it's that improbable, but we cannot rule that out because the mere fact that we are here still doesn't rule out the possibility that this is the only place we're here. If there is only one planet in the universe that has life, then that one planet has to be this one. We know that with hindsight. Well, you laugh, but it's actually quite a profound point. It means that well, let me put it another way. Suppose we decided that because we've never been visited by aliens, or more probably by radio waves from them, suppose we said this means it's very unlikely that there's life elsewhere, then if any chemist came up with a theory for the origin of life that seemed plausible, we would have to say, that's very worrying. We shouldn't be looking for a plausible theory. The theory we're looking for has to be a deeply implausible theory. Unless, I mean, there is a way of wriggling out of that, unless getting something like bacterial life is easy. But then getting intelligent life capable of building radio transmitters is
Well, I'd like to come on to that in a moment, but first I think we need to deal with one question that often comes up when I'm talking about this sort of thing at dinner parties, and people say, oh, but aren't we on the verge of making life in the lab? Won't we have life in a test tube within a few years? And you do sometimes see what I think are somewhat misleading newspaper headlines to that effect. But supposing that were the case, supposing that sometime in the next 10 years somebody makes life from scratch in the lab, it's still not going to tell us how Mother Nature did it without a budget and a lab.
That's right.
And,
I mean, I think it would be...
And also having a plan of action.
I agree. I think it would be not... I mean, it would be extremely interesting if Craig Venter or somebody who's coming on after us, I think, isn't he? So,
he is.
Yes.
Right.
Makes life in that sense, but it would be a DNA-based life. I mean, what would be really, really interesting would be if somebody made a completely different kind of life which had its own replicating molecule, which was not DNA, or perhaps nothing like DNA.
Well, would you like to speculate a bit?
No, because I'm not enough of a chemist. I mean, it's a question that I'm continually asking chemists. Please sit down and throw away all preconceptions and devise an entirely alternative biochemistry, and then see how many degrees of freedom have you got? I mean, could you dispense with protein, for example, and use a completely different kind of molecule to do the job of protein? Or could you dispense with nucleic acids, which is the family of chemicals to which DNA belongs? Could you imagine an entirely different and alternative kind of replicating entity?
And could you have a molecule that did the job of both, the same class of molecules that were both informational
Well, that's a very
molecules
interesting, because that gets us close to the catch-22. As you know,
the chicken and egg problem.
Yeah, that's right. It's been suggested that perhaps I should back up and say what these roles are. I've already said the role of DNA, which is to act as the coded information, the memory, the replication, the information that goes through from generation to generation. What protein does is act as the executive branch. It's the hardware that actually builds bodies and makes them do what they do. And the system works so beautifully because proteins can assume an almost indefinite variety of shapes, literally three-dimensional shapes, and the shape of a protein molecule, the three-dimensional shape into which it coils up, is determined by the one-dimensional sequence of building blocks of protein, which are amino acids. And that one-dimensional sequence of building blocks of amino acids is determined by another one-dimensional sequence, that of the DNA. So the DNA is a one-dimensional coded strip of information. It's translated by a very, very simple lookup dictionary into a one-dimensional sequence drawn from only 20 amino acids. The protein chain, the chain of amino acids, then coils up into a shape which is determined by that one-dimensional sequence, which is in turn determined by the one-dimensional sequence of DNA. And that three-dimensional shape determines the properties of the protein, in particular, its capacity to catalyze, to speed up hugely, one particular chemical reaction. So the chemical reactions that go on inside a cell, it's rather different from the chemical reactions in a chemistry lab where all the chemicals, all the reagents are stored in separate bottles and they never meet unless a chemist pours them into the same test tube. In the cell, all the chemicals are just mixed up together as though some vandal had come and poured all the bottles from a chemistry lab into one great big vat. But they don't react together until they get the right enzyme, until they get the right protein. And that's what is the equivalent to the barriers between the glass bottles. So every cell, a liver cell or a kidney cell or a muscle cell, will have different enzymes activating particular chemical reactions. And the enzymic activity, the catalytic activity of a protein is determined by its three-dimensional shape. And that's determined by the genes. So proteins have a very, very, very special role to play in earthly life. And we don't know whether there's anything else could do that. But you raised the question of whether there are some molecules that can play both roles, both the protein role of being a catalyst and the DNA role of being replicating information. And RNA, which is a rather similar chemical to DNA and which is much implicated in the transactions between DNA and protein, RNA does have, at least in rudimentary form, the catalytic, something like the same catalytic qualities as protein, and it also has something like the replication qualities of DNA. So the great hope of people in your field, now I'm telling you your own field, is that RNA might be the bridge, might solve the problem, the catch-22 problem, by being capable of both the DNA role, the replication, and the protein role, the catalytic role. So many of the modern theories of the origin of life center on RNA as the possible precursor.
Now these molecules are all in effect one-dimensional. As you say, the proteins roll up into three-dimensional shape, but everything starts out as digital information in one dimension. Could we imagine that life might do it in two dimensions? After all, the disk in my computer is a two-dimensional thing.
I think I could imagine a two-dimensional genome. What I can't imagine is a three-dimensional genome. That doesn't mean that it couldn't exist, but the point about one and two dimensions is that it's very easy to read out the information. In the case of one dimension, like DNA, it's like a tape passing through a reader, and that's exactly what you see. Actually, it's been translated into RNA by the time this happens. So the DNA is is transcribed into RNA, and then the RNA passes through a reader, just like a tape passing through a tape reader. Actually, the tape reader moves along the tape, but apart from that, it's the same. Now, a two-dimensional genome could work pretty well. I mean, you just imagine scanning across or reading it in some way. Three-dimensional, it's very hard to imagine, because how would you get a copy? How would you make a copy of a three-dimensional object? It's not easy to imagine. So protein works in a world of three dimensions, which is why, which I think more or less precisely why, protein itself could never have been the self-replicating molecule. Two dimensions I could imagine.
Let's come on to talk about once that great first step is accomplished and life gets going. We're talking now about the possibility of weird life, the alternative forms of life, and we might find weird life on other planets. We don't know, because we don't know what the probability is, as you've said, that life will get going in the first place. But once it does get going, everybody wants to know, well, is there going to be intelligent life out there? And we're now faced with the same or a similar problem, that we find it very hard to put a figure to how likely it is that something like intelligence will evolve, given that life gets going. If we've got some sort of microbes, come back a few billion years later, will there be radio telescopes? Now, I know it's unfair because, again, I'm saying, do you have an intuition about this? Do you think that if there is life, say, throughout the galaxy, throughout the universe, that there are going to be many cases of intelligent life, or are you, like me, just prepared to say, well, maybe, maybe not?
Pretty much. I mean, we have one very, very weak piece of empirical evidence, which is that we've not yet been visited. So if intelligent life were really very, very common, then you might expect that not they themselves would be here, but yes, their radio signals might have been picked up.
This is called Fermi paradox.
Yes, Enrico Fermi, the great physicist, was once at lunch with two physicist colleagues, and he suddenly said, "Where is everybody?" And his colleagues, it seems, immediately knew what he meant, which is rather remarkable. He meant why haven't we received any visitation by presumably by radio waves? The universe is so vast that there could be islands of life dotted around the universe to a very large number, but yet because the universe is so vast, it could be that each island remains in perpetual ignorance of its neighbors, which would be rather sad. When I was making the argument about the possibility that we are the only form of life, I think I'll stop there.
But it does raise this really important point, and I don't know if there's a yes/no answer to this, but the essence of Darwinian evolution is that nature can't look ahead, can't anticipate, that it's exploring the space of possibilities, and what works at the time, and that's it. And so I think a lot of people have this notion that intelligence is such a wonderful idea that somehow nature would march towards it and sooner or later would discover it. And yet we have no reason to expect that. On the other hand, if in evolution, once nature does discover a good thing, it does tend to make more of the same. There is a sort of amplification factor, isn't there? Could we see intelligence as of that category, that you discover a little bit of it by accident and you think, well, that's really good, let's make more of it, more of it, more of it, and we're not the end product, but...
Yes, I mean, when it arises by natural selection, and we know it arose at least once in our cells, it had to have been useful for the propagation of genes in the first place. I mean, there had to be some benefit in growing bigger and bigger brains. And so you've got to think of a way in which it's, in a mundane, utilitarian way, useful to begin with. Now, you said quite rightly that natural selection has no look-ahead capacity. It doesn't... you're never allowed in framing Darwinian arguments to say it would be a good thing because in the distant future perhaps we can foresee that the species is going extinct. So let's all ration our selfish greed so as to stop the species going extinct. You're not allowed to make that kind of argument in the ordinary Darwinian context. And it may well be that many a species has gone extinct precisely because there was no look-ahead facility. But once you get a brain that's big enough to do that, then it is possible to look ahead. And I just remembered a lovely satirical remark by Sidney Brenner, the great molecular biologist, where he was castigating people who think of natural selection as looking ahead. He said, you can't imagine that life forms in the Cambrian era might have selected a particular chemical because it might come in handy in the Cretaceous. but I mean, you are right that once brains become big enough to look ahead, maybe natural selection in the ordinary sense wouldn't favor it, but technology can take over. You start making complicated machines. You start developing books and computers, and a whole new kind of evolution gets going.
But it just interests me as to whether or not we really could expect some fraction of other worlds that may have life on them, starting out with simple microbial life, some fraction that might have intelligence, and what that fraction might be, whether intelligence is one of those things that is such a good idea that it's really quite likely to be discovered time and again, or whether it's just a quirky little thing that happened on this planet, and we think it's important because, you know, that's our thing. We feel that that's the defining characteristic of humans. But as my friend Charlie Lineweaver likes to remind me, you know, elephants probably think having a long trunk is the supreme quality, and they would look back in evolution and see evidence for a directionality towards longer and longer, whatever the plural of proboscis is.
Yes. I mean, we can look around. We've got a lot of information about life forms on this planet, and so it's an interesting exercise to make lists of those features which have evolved many times and those features which have evolved only once. And it's been calculated that eyes have evolved at least 40 times independently. So it looks as though there's plenty of pressure to evolve eyes, and you could say that eyes are likely to evolve maybe only on this planet, but quite likely on any planet where there's light and where you don't live in a perpetual fog or something of that sort. But intelligence and language, it seemingly have only evolved once. I mean, we can look around the different mammals and we see lots of examples of flying, of gliding, of digging, of swimming, of eyes, of ears, echolocation, but not intelligence, not language. So I think already we can say that at least on this planet, intelligence and language are not in the same category as eyes. I wouldn't say that rules it out on other planets at all, but it perhaps is
But it
less...
means it's something that it's hard to discover, if I could put it that way.
It may be a bit hard to discover, yes.
As
Yes.
harder than flying or seeing might be. Now, as we're getting speculative, we've been talking about these universal Darwinian principles, but Darwin's theory wasn't the only theory of evolution, was it? Lamarck had a theory which is out of favor, but it's a scientific theory which would have very different properties.
Yes.
Might we find a planet where Lamarckian evolution reigns supreme?
Yeah, I thought a bit about that. I think the answer to that is no. The Lamarckian theory, what we're looking for in a theory of evolution is something that can explain adaptation, something that can explain the illusion of design. Why do animals, why do lineages get better at doing what they do? And Lamarck's theory was that they strive to do it better. And the classic example is the giraffe striving to reach the topmost branches of a tree, and they stretch the neck and stretch the neck and stretch the neck. So the neck gets longer because it's being stretched by the desire of the giraffe to reach the topmost trees. And then Lamarck had this idea of inheritance of acquired characteristics. A lot of people believed that you inherit those characteristics which you acquire during your life. That we now know is not true. But some people have suggested that if only it was true, and maybe on some other planet, it will turn out to be true. Maybe that the system of heredity is such that whatever, if you exercise your muscles during your lifetime and they get bigger and stronger, then your children will be born with a head start in the muscle department. Now, if that were true, some people say, couldn't you have a form of life which didn't use Darwinian principles at all, but used Lamarckian principles? I don't think it would work, actually, even if acquired characteristics were inherited, because the subtlety of adaptation, for example, if you take the eye, which has these immensely complicated, detailed features where every little detail improves vision, it's not plausible that the more you use your eye, the better it gets. I mean, there are a few things where you could just about say that. The more you use your biceps muscles, the bigger they get. But the more you use your eye, the more photons wash through the lens. That doesn't make the lens get clearer. It's very hard to imagine a large number of features which will improve with the using. Whereas on the Darwinian principle, every little tiny detail, no matter how subtle, no matter how small, no matter how deeply buried inside the animal, anything that improves the way the eye works or the liver works or the spleen works, whatever it is, no matter how detailed, no matter how cryptic, no matter how concealed from the outside world it is, if it improves the chances of survival, that's good enough. Natural selection will grab the gene that made it. So I would be skeptical of Lamarckian evolution producing anything but extremely crude, possibly muscle-bound creatures.
Now we're running out of time, and I think Lawrence is gesticulating, but I can't see because the lights are in my face, whether he's saying carry on or stop now. But according to my timing, we should be winding this up pretty soon. He's disappeared. Well, we might as well carry on. He did threaten that he'd come and bodily drag us off the stage if we...
5 minutes.
He's saying 5.
Oh, 5.
You
Okay.
have some questions for 5 minutes. Sure, why not?
Right. Well, that's probably a good time to invite one or two people to come forward to the microphones, which you will see, I think, on either side, to ask some questions. Could you keep the questions as short as
Could
you
we
can?
have the lights up so we can see the audience?
And the usual admonition, questions, not statements, please. So we'll start with the gentleman over there.
Sorry to move it away from biology somewhat, but I'd like to pose a question about your stance on religion, as we've seen in the God Delusion and various other programs and talks. I'm at Animal School myself at the moment, so I think that the chapel services have had the same effect on me as I believe they have on you. So I sympathise and I agree with you, but do you not think that possibly the way you've been putting across your point, it's almost aggressive? I know that you've been called...
Yeah, no, I think, can we just keep it to that?
Sorry.
I think we got the point.
Sorry, yes.
Well, Richard, do you want to get drawn into this, or?
Well, it has
or
nothing
should
to
we...
do with what we've been...
No, I mean, I would
let me try
prefer
to
a question on the content of the presentation, in particular on the origins theme. Could we just put that one on one side for the moment and perhaps go over to here? Do we have a question on biology, on origin of life, origin of species?
I was wondering if you, what your views on the last universal common ancestor is. Like, is it possible...
Could you speak a bit louder?
Your views
sorry.
on Luca, the last
Luca,
universal
yeah.
common ancestor.
Is it
Okay.
possible that there might be more than one, like, originator of life, and maybe
Okay. The last universal common ancestor is the common ancestor that all living creatures today can look back on as our shared ancestor. It is not the same, or probably not the same, as the first living thing of all. So you could imagine that the first living thing of all had offspring and maybe quite a lot of branched descendants, but all of those have died out, and we, by which I mean every living creature alive today, traces back to Luca, the last universal common ancestor, which lived maybe 500 million years later than the very first organism of all. Well, I suppose the interest of that question is whether life originated, one part of the interest is life could have originated more than once. There could be more than one entirely independent origin of life. If you look at every creature that's ever been looked at so far, we have an enormous amount in common. We all use either DNA or RNA as our genetic system. Above all, we all have the same genetic code, almost literally the same, with one or two tiny differences, which translate the sequence of base pairs into amino acids. Now that suggests that we are all descended from one common ancestor, but it does not rule out the possibility that there were different origins of life, and Paul is the leading champion of the idea that there may even still be descendants of independent origins of life, which might have completely different genetic code, for example. And he makes the very reasonable point that nobody's looking for them. And it may be that if you look hard enough, you may find a totally different kind of, maybe something like a bacterium, which uses a totally different machine code indicating a completely independent origin of life.
Okay, thank you. We'll take a question on the right here.
Yes. What if, in fact, we find that there is intelligent life on other planets? Has been documented in even that there are 14 planets with human life, but they, in fact, are hiding from us because they feel we are not acting in a very intelligent manner, rather than reaching.
Okay, thank you.
I mean, yes.
Not to make you think that I'm that weird life form that may appear.
I find it entirely plausible, but I've nothing to add to this amusing suggestion.
We probably have time for only one more question, and so I'll take that from this side.
Could you please comment on epigenetics? Just very interested in understanding what your feeling is on that and the switching on and switching off of genes and how that might relate to Darwin's theory.
There is a very trendy recent tendency in genetics called epigenetics, and it is sometimes regarded as somewhat tantamount to Lamarckian inheritance of acquired characteristics, which it isn't. There is some evidence that genes can become altered during an individual's lifetime and get passed on to the next generation. It doesn't seem to go on for an indefinite number of generations, which is the absolute prerequisite for it to be of interest to Darwinian evolution. These are things like maternal effects, which last for a couple of generations. They are interesting, but I suspect they're not as interesting as many of the proponents of the idea think.
I just need to check with the boss that we really are out of time. Yes, we are. Ladies and gentlemen, it's been a great pleasure for me to just sit here and throw out a few questions and to listen to the way Richard has dealt with them. It's always fascinating to hear his expositions. I hope that you will join me now in thanking him very much indeed, and prepare yourself for the next event. Of his latest book, The God Delusion. So Richard recently retired, would you believe, although he tells me that doesn't mean very much, as the first Charles Simonyi Professor of the Public Understanding of Science at Oxford University, where he's also a Fellow of New College. I think Richard is arguably the foremost science communicator in Britain and possibly the world. His best-selling books are bought in their millions, and you'll know the titles like The Selfish Gene and The Blind Watchmaker. They've influenced a huge number of people. His twin scientific and literary accomplishments are recognized by the fact that he's both a Fellow of the Royal Society and a Fellow of the Royal Society of Literature. His eagerly awaited next book, The Greatest Show on Earth, The Evidence for Evolution, will be published later this year, and I do hope he can make a return visit as part of the launch of that book. I should also mention...
Hello again. Thank you. Thank you. Thank you very much. Welcome again to some of you who've been here this morning, and to those who've just arrived, welcome. I'm Lawrence Krauss, Director of the Origins Initiative here, and while I know a number of you were here, I think some of you have just come for the afternoon, so I'll spend a few moments talking about what's been happening here. The Origins Initiative is designed to ask some of the deepest questions that people have ever asked. In fact, in the morning we heard about how people started to ask questions. And when they first started to come up with symbolic language, they probably asked, why am I here and where did I come from? And those are the kind of questions the Origins Initiative is dealing with. And we've had 70 of the world's greatest scientists here over the weekend debating and discussing some of those questions. But this is truly the capstone event. It's bringing together, and I truly believe, the largest accumulation of scientific public intellectuals that have ever been in one place at one time. And we are particularly honored to have them here. And it's been an exciting morning. And also, as I said this morning, I'm particularly proud to be here for so many reasons. But one of the reasons is first my colleague and friend, Paul Davies, who is a very distinguished physicist in his own right and also popularizer of science as well, and is probably well known to people here and everywhere. And I owe him a special debt of gratitude because, in fact, about a year and a half ago, he invited me to come here to give a lecture, and that led to my moving here. And his presence here, in fact, was a huge factor in attracting me. So I'm very happy to introduce Paul Davies.
Well, ladies and gentlemen, good afternoon and welcome to the second major session of this spectacular series of presentations. And it's my honor and pleasure to welcome back to the Gamage Auditorium Professor Richard Dawkins. Richard was here last year. Some of you may have attended his presentation when he spoke as the 2008 Beyond Annual Lecturer on the theme of...
...is that we have a 3,000 seat auditorium that's essentially sold out for 12 hours of science. And I think that says something about the people of Phoenix. So I want to applaud all of you. So thank you. It's my great pleasure now to introduce, to welcome you on behalf of Arizona State University, Betty Capaldi, who's the provost of the university. And in case you don't understand what a provost is, in my case, it's very simple. She's my boss's boss's boss. So, okay.
Thank you. Welcome to this absolutely fantastic symposium. It's been a terrific few days of science, and now we're to the public portion. I think this type of event shows why it's so wonderful that ASU is here in Phoenix. I think you know some people have some difficulty understanding the value of a research university. Of course, we educate the students, which is part of this event. They did an event at high school this week, and our students can see this, and we're also being broadcast on the World Wide Web. But bringing the most cutting-edge minds on the most important ideas of the day to Phoenix, and to have a public event so that you can learn about these issues and be up to date, because you influence policy, you influence decisions, and we really appreciate that you all came here for this event. This afternoon is going to be very exciting. We have first some discussions by Richard Dawkins, and then Craig Ventnor and Lawrence Krauss. Lawrence, who you just saw, is the creator of this entire event and has done just a fantastic job. And then Ira Flato will moderate a panel with 6 Nobel laureates. So I know you will enjoy it and be very well informed. Thank you very much for coming. Lawrence is coming back now.
Thank you. Thanks, Betty. Thank you very much. Thank you. Thank you. Well, as I indicated, before the break, we had a dialogue, and we're going to have one after the break, so it's not all lectures. And I'm very pleased to introduce